Hey everybody, just a quick video to run through this calorimeter question where we've got steam entering the calorimeter, which is going to change state and then cool down. We've got water and the calorimeter, which are going to heat up in response to this. So the basic formula we're going to use is energy lost is equal to energy gained. So if you're checking your work for this, make sure that you have energy loss is equal to energy gained written out, because they often will specifically give marks for saying that, as simple as it may seem. Then the energy that's going to be lost is going to be lost by the steam. So we have ml here because the steam is going to change state first. So our specific latent heat formula. Then mc delta theta, because that steam is going to be turned into water. Then it's going to be water at 100 degrees Celsius. It has to cool down to its final temperature. On the right hand side, we're going to have the things that gain energy. So that will be the water as it heats up. So we have the specific heat capacity of water formula. And the copper as it heats up, so we have the specific heat capacity of copper formula. So we're going to fill in the different values here. So the mass of the steam is 0.005 kilograms. Specific latent heat of vaporization is 2.26 per 10 to the 6. Our mass of steam, again, is 0.005. It's going to have the same mass when it's converted from steam to water. Specific heat capacity of water now is 4,180. Then the change in temperature of the steam, it's going to go from 100 degrees Celsius down to its final temperature, which we do not yet know. That's what we're trying to find in this question. They want us to find the final temperature that the steam and the water balance out at when they're added together. On the right hand side, our water is going to gain energy, so 0.115 is the mass of the water, 4180 is the specific heat capacity, and then for its change in temperature, it's going to be the difference between the final temperature and 22 degrees, where it originally started from. Same thing then for the copper calorimeter. Its mass times its specific heat capacity times its change in temperature, which again will be the final temperature take away 22 degrees. Now we only have one unknown in this equation, even though it comes up a couple of times. That's our final temperature here. So we just are going to use our algebra skills as well as we can to try and figure out what that theta value is. Now, even if you get to this point and you don't get all the algebra done, you've still got a lot of attempt marks if you wrote out energy lost equal to energy gained. You wrote out your more detailed equation where you've subbed in ml and mc delta theta for changes in state and when things are heating up or cooling down. Okay, so I multiplied 0.05 times 2.26 million. I got 11300. Where I multiplied 0.05 times 4180, I got 20.9. Where I multiplied 0.15 times 4180, I got 40.7. And where I multiplied these two numbers, I got 27.3. So I left my left hand side alone then for the next line, and I just focused on the right hand side. Here I've got 480.7 times theta minus 22 plus 27.3 times theta minus 22. So for the sake of making life easier on myself, I used a little algebra trick, the same way that 3x plus 2x, we can just add the numbers in front of them. Will give us 5x. If I've got 480.7 times theta minus 22 plus 27.3 times theta minus 22, because these numbers here are the same, I could just add the coefficients. It's a fancy word for the numbers in front of those brackets. So 480.7 plus 27.3 add together to give me 508, and then I just keep the theta minus 22. Again, it's the same thing as adding 3x plus 2x. Just add the numbers in front and then keep the thing that they're multiplied by afterwards. If you want to do them out in a more long-winded way, then you're absolutely entitled to multiply 40.7 times theta, multiply it by minus 22, and then do the same thing over here. You'll just end up with 4 terms when you multiply them out instead of 2 terms. You'll actually see I do it over on the left-hand side here in a second anyway. Okay, so then on the left-hand side, if I multiply 20.9 times 100 and multiply it by theta, I end up getting 2090 and minus 20.9 theta. My 11300 is still over here. Then I multiply 508 by theta and 508 times minus 22, and I get 508 theta minus 11176. At this point now, we're really just trying to bring all of our unknown terms over to the left hand side, and all of our known terms over to, all of our unknown terms over to the left hand side, and all of our constants over to the right hand side. So that's what I do. Bring all the unknowns over to the left. I've got minus 20.9 theta, minus 508 theta. The 20.9 was already on the left, so it kept its sign. But the 508 theta moved from the left to the right, so it lost its sign and got the opposite sign instead. So again, the 508 theta moves to the other side of the equals, so it becomes a minus. Its sign flips. On the right hand side, we keep the 11176. It's staying where it is, so it keeps its sign. 11300 comes over, so it gets a minus. Its sign flips, and the 2090 comes over, so its sign flips. Simplifying these two terms, I get minus 528.9 theta. Simplifying these three, I get minus 24566. And then I just divide both sides by minus 528.9, and that gives us our final answer there of 46.447 degrees Celsius. I kept 3 decimal places because, again, if you're not sure or the question doesn't make it obvious, 3 decimal places is a good general guideline.